Vision and Eye Health, Understanding the Marvel of Sight. The human eye is one of the body's most sophisticated sensory organs, functioning as a biological camera that converts light into electrical signals for the brain to interpret. This complex process involves multiple components working in harmony. The cornea and lens focus light, the iris controls light intake, and the retina, lined with photoreceptor cells, rods and cones, transforms light into neural signals sent via the optic nerve to the visual cortex. However, this delicate system is vulnerable to various disorders that can impair or destroy vision. Cataracts, clouding of the lens, blur vision like a fogged window. Retinal detachment creates emergency vision loss as photoreceptors lose oxygen. Optic nerve damage, from glaucoma or trauma, severs the brain's visual data cable. Myopia progression, exacerbated by prolonged close-up screen use, elongates eyeballs abnormally. Modern lifestyle factors, particularly excessive nearwork, phones, computers, and blue light exposure, are driving a global myopia epidemic, with half the world projected to be nearsighted by 2050. Children who spend less than 1 hour outdoors daily have 2-3x higher myopia risk. Protecting our vision. 20-20-20 rule. Every 20 minutes, look 20 feet away for 20 seconds. Outdoor time, 2+ hours daily helps prevent childhood myopia. Regular exams, catch glaucoma, diabetic retinopathy before damage occurs. While advanced treatments, laser surgery, retinal implants, exist, prevention remains paramount for preserving this irreplaceable sense that connects us to the world. Life after vision loss, psychological and adaptive challenges. The sudden or progressive loss of vision creates profound psychological and physiological disruptions. Initially, individuals often experience grief similar to bereavement, with 30% developing clinical depression. The absence of light perception also disrupts circadian rhythms, leading to chronic sleep disorders as the brain loses its primary light-based timekeeping signal. Adaptation requires neurological rewiring. The brain must reorganize to prioritize other senses. Auditory processing sharpens dramatically, enabling echolocation skills, detecting objects through sound reflections. Tactile sensitivity increases, allowing braille reading at speeds exceeding 100 words a minute. Spatial memory expands, with many developing mental maps accurate to within centimeters. Modern assistive technologies bridge some gaps. AI-powered apps describe surroundings through smartphone cameras. Haptic navigation devices use vibration cues to signal obstacles. Retinal implants can restore limited vision for select conditions. Yet societal barriers remain problematic. Only 12% of public websites meet accessibility standards. Urban environments often lack tactile paving or audible signals. Workplace accommodations remain inconsistent. The way forward. Early intervention programs to teach adaptive skills during neuroplasticity peaks. Universal design principles in public spaces and digital platforms. Mental health support addressing vision loss trauma. Biomedical research into optic nerve regeneration and bionic eyes. With proper support, many achieve remarkable independence. Blind programmers code using screen readers, and visually impaired scientists continue research through adaptive technologies. The challenge lies not in the individual's capacity to adapt, but in society's willingness to accommodate different modes of perception. The miraculous adaptability of the human brain. The phenomenon of neuroplasticity in individuals with visual impairments reveals one of the most extraordinary capabilities of the human brain, its ability to fundamentally rewire and repurpose itself. When congenital blindness occurs, the visual cortex doesn't remain idle. Instead, it gets recruited to enhance other senses in remarkable ways. Groundbreaking fMRI studies show. In people blind from birth, the visual cortex becomes highly responsive to sound and touch, processing auditory cues with 3x greater precision than sighted individuals. This cross-modal adaptation is most dramatic when blindness occurs before age 7 to 10, when the brain's plasticity is at its peak. Late-onset blindness shows more limited reorganization, proving there's a critical window for neural repurposing. This neural flexibility enables astonishing abilities. Echolocation experts can detect objects as small as a golf ball through click echoes. Braille readers show tactile processing speeds comparable to visual reading in sighted people. Blind musicians often develop perfect pitch at rates 10x higher than sighted peers. Implications for science and rehabilitation. Therapeutic potential. Understanding neuroplasticity could help stroke recovery and neurodegenerative diseases. Education strategies. Early intervention maximizes sensory compensation. Technology design. Brain-computer interfaces could harness this repurposing capacity. The blind brain doesn't just compensate, it transforms limitations into new perceptual capabilities, challenging our fundamental understanding of sensory processing. This remarkable adaptability underscores that what we call disability often represents the brain's incredible capacity to find alternative paths to experiencing and interacting with the world. Fundamental differences between congenital and late-onset blindness. The experience of blindness differs profoundly depending on whether it occurs from birth or later in life, revealing fascinating aspects of human perception and cognition. For those with congenital blindness, the brain constructs an entirely non-visual framework of reality. Their mental representations derive from synthesizing auditory, tactile, and spatial information into unique conceptual maps. Key contrasts emerge. Mental imagery. Congenitally blind individuals create abstract spatial models, like seeing a room through echo patterns. Late blind individuals retain and manipulate vivid visual memories, though these gradually fade over decades. Language processing. The congenitally blind understand color and metaphors through multisensory associations, example red linked to warmth or warning sounds. Those blinded after childhood maintain literal visual references for years. Navigation strategies. Early blind people develop superior path integration skills using proprioception and sound cues. Late blind individuals initially rely on remembered visual layouts before adapting to non-visual methods. Neurological research shows congenital blindness leads to permanent cross-modal reorganization of visual cortex function. Late-onset blindness involves competitive plasticity between fading visual memories and new sensory inputs. The age cutoff appears around 10 to 12 years, after which the brain loses much of its capacity for complete sensory reassignment. This dichotomy demonstrates that vision isn't just about eyes, it's about how the brain learns to process spatial information, with lifelong implications for rehabilitation approaches tailored to when blindness occurred. The triumph of human perception, seeing without eyes. The human experience of blindness reveals a profound truth. Vision is not merely a biological function, but a dynamic cognitive process that can transcend physical limitations. When light fades, the brain orchestrates an extraordinary sensory symphony, transforming echoes into landscapes, vibrations into images, and memories into vivid mental panoramas. 3 remarkable adaptations demonstrate this. Echolocation mastery allows some blind individuals to perceive minute details, discerning material density, distance, and even color shades through sound reflections. Tactile vision substitution systems convert camera inputs into electrotactile patterns that the brain learns to interpret visually. Crossmodal dreaming, where congenitally blind people experience rich spatial dreams through sound and touch sensations. Neuroscience confirms these aren't mere compensations but genuine perceptual transformations. fMRI scans show blind experts using visual cortex areas for complex auditory processing. Cognitive tests reveal equivalent spatial reasoning abilities between sighted and blind individuals. The brain's pattern recognition systems remain intact, they simply process different input channels. This adaptability carries profound implications. Challenges our sight-dominated understanding of consciousness. Proves perception is fundamentally about information processing, not sensory modality. Suggest all humans possess latent capacities for alternative modes of perception. The blind experience ultimately teaches us that vision resides in the mind, not the eyes. A lesson in human potential that illuminates how all brains can find extraordinary ways to know and navigate their worlds.